All right, this is the first of a four-part series on the force table equilibrium lab. And so I basically have set up here, I have hanging mass with three different hanging masses, magnitude of force, direction, and length of drawn vector. I think it can be seen clearly. Now, right now I have data set down. Now you might consider this to be results, and we'll talk about that in just a second, but this is a sample of data from a typical lab, part A, where you have three different forces. Now, first off, let's talk about this right here. Notice that the units here are kilograms and not grams. That when you're actually looking at the masses that most of you are using, they were in grams. And so, just as for instance, if it's 100, and let's see if we can go something a little bit darker. If I have a 100-gram mass, and again I want to emphasize that if it is in grams, it is a mass. It is not a weight or a force of any type. If it's 100 grams and I want to put it into kilograms, then kilo means 1,000. And so 1,000 has 3 zeros, so I need to move it 3 places. Now, which way to move it? A gram is really tiny. A kilogram is relatively large. My mass is about 90 kilograms, actually at this point. It's probably about 95 kilograms, but I'm going to go with 90. I'm living in the past. My mass is about 90 kilograms, or about 90,000 grams. If you think about it that way, that 90 kilograms, kilo means 1,000. And so this would be the equivalent of 90, just substituting, instead of kilo, I write 1,000, 1,000 grams. So if I'm going from grams to kilograms, I need to move the decimal point to the left. So I have fewer of them. So I move it over 3 spaces, 1, 2, 3. And so 100 grams is the equivalent of 0.100 kilograms. Now, so over here, this would be the equivalent of a 100-gram mass, or point, that's a decimal point right there, 0.100 kilograms. This is 150 grams, or 0.150 kilograms. Again, big old decimal point right there. And here, 200 grams, or 0.200 kilograms. Now, the main point of this is to try to figure out the magnitude of the force. Now, in our particular situation, we have, let's take one particular string. I've got my central object here. That was the twist tie for most of you. I think it was actually a metal ring for one group. It's going over a pulley and hanging down like this. I have a mass hanging on the end of a string. That's my pulley. My mass is hanging on the end of a string. I have two forces acting on this mass. I have a force of gravity acting down, F sub W for weight. I'm going to write that bigger just so that it shows up a little bit better. I have weight acting down, and I have tension acting up on the rope. So I have tension up, weight acting down. And so if this mass is just hanging there, if it is in equilibrium, in other words, if the mass is not accelerating, then the forces up must equal the forces down, similar to that last problem on the quiz. So I know that the tension must equal the weight. Well, the tension in a rope, and this is an assumption that we are making, the tension in the rope is constant throughout the whole thing, as long as the mass of the rope is insignificant, as long as this is parallel to the table, and there's no friction in the pulley, then the tension in the rope should stay constant. Now, these are all these are assumptions that we are making here, but it is close enough for actually through. We might get into some problems in Physics 251 where we get rid of one of those assumptions, but at this point, it is a good enough approximation. So the force acting on the ring here from this is basically, it's a tension acting this way. I'm assuming that the ring is so little mass that I'm not worried about the weight, about it being pulled downwards. Basically, we have a tension acting this way. So I have a tension acting this way, it's equal to that tension. This tension is equal to the weight. And so the formula for weight is equal to the mass times the acceleration due to gravity at that particular location. Now, acceleration due to gravity is not the same everywhere on Earth. It's not the same everywhere in the universe. It is not a constant. However, if you're near the surface of the Earth, it's about 9.8 meters per second squared. And so, define the magnitude of the force. And again, the magnitude of the force is the tension. Tension is equal to the weight. Weight is equal to mass times acceleration due to gravity. And so all I have to do is take this mass and multiply times 9.8 meters per second squared. So times 9.8 meters per second squared. And the magnitude of the force is 0.98 newtons. A newton is a kilogram meter per second squared. And so this is 0.98 newtons. 0.2 is 1.96 newtons. And this would be 1.4. Let's see how many that says. That's 0.497. 1.47 newtons. And again, decimal point here, drawn it bigger just so it shows up on the videotape. All right, so that is the first part of this. The magnitude of force is equal to the weight. Ultimately, it's the weight hanging off the end. And so I have to figure out what is the weight of this mass, and it involves multiplying times 9.8 meters per second squared. All right, part 2 coming up soon.